Hi everyone, I'm Harsha. Thank you for the introduction. I am a fourth-year PhD student at Waterloo. I'll be presenting our paper, VectorCDC, Accelerating Data Deduplication with Vector Instructions. This work was done in collaboration with Abdelrahman and our advisor, Professor Al-Kiswany at the University of Waterloo. Okay, so the amount of data generated and stored on the cloud is growing at an explosive rate. Cloud storage providers such as AWS, Google, and HP are relying on numerous mechanisms to support this data influx. Some of these mechanisms are distributed file systems, novel storage architectures, and data deduplication. So what is deduplication? Deduplication is a mechanism that is used to identify and eliminate duplicate data to conserve network and storage costs. It consists of numerous phases that a lot of the authors before me have talked about and explained very well, so I'm just going to speed through this with an example. So here's the interaction between a client and a server, both of whom want to store files in a deduplicated fashion. The client first takes its file, divides it into chunks, and hashes them to get fingerprints. It then asks the server, have you seen any of these fingerprints, H1 to H3, before? In this case, the server hasn't, so it says, nope, send me all the fingerprints as well as their corresponding chunks, which the client does. When the next client comes along with another file and repeats the same process to end up with fingerprints H1 and H4, you see that H1 has already been seen before by the server. So when it asks the server, have you seen H1 and H4, the server says, yep, I already have the chunk for fingerprint H1, just send me the chunk for fingerprint H4. In this way, you're eliminating the duplicate part between both the files, which is the chunk for fingerprint H1, and you're only storing the non-duplicate part. Now, as we can see, one of the critical phases here is dividing files into chunks. And as you can imagine, there are numerous algorithms to divide files into chunks. They can be classified into two families, hash-based algorithms and hashless algorithms. Now, this file division or content-defined chunking is a very computationally intensive process. And our idea with this paper is to accelerate it with SIMD, that is AVX or SSE CPU instructions. Now, there is an existing approach to do this, and they accelerated hash-based algorithms with AVX 512 instructions. This graph here shows you speed on the y-axis and chunk sizes on the x-axis. And the pattern bars are accelerated versions of the solid bars. For example, CRC's accelerated version with AVX 512 instructions is SSCRC. You'll notice that the speedups that are achieved despite using AVX 512 instructions are pretty low. They're able to achieve 1.2 to 1.8x at maximum, right? And why is this? This is because hash-based algorithms are inherently hard to parallelize. They have dependencies between adjacent bytes. So many of you may be familiar with Rabin's chunking, and you slide a window over the source data and recompute hashes. But as the window moves, the new hash value is a function of the old hash value, the outgoing byte, and the incoming byte. So you see that there's a dependency between adjacent bytes. To work around this, the paper I just talked about processes different regions of the file in using one SIMD instruction. But to do this, they need to resort to using expensive scatter and gather instructions, which causes the low speedups I just showed you in the previous slide. So what do we do differently? In VectorCDC, we choose to accelerate the other family of CDC algorithms, which is hashless CDC algorithms. We use AVX-friendly tree-based search and pack scanning methods, which I'll talk about later today, to accelerate these algorithms. We are compatible with a wide range of existing approaches. And using our methods, we're able to achieve 21 times higher throughput over SSCDC, the method I just talked about. And most importantly, accelerating hashless algorithms with our method has no negative impact on deduplication space savings. Okay, so now that I did my sales pitch, let's talk a bit about the background, both in terms of hashless CDC as well as vector instructions, and then move ahead to the design and evaluation of our paper. So what is hashless CDC? There are multiple CDC algorithms that can be classified as hashless. Some examples are shown here. Let's look at RAM and see how it works. So the main objective is to divide files into chunks. And to do this, RAM first begins by picking a fixed size window at the beginning of each chunk, identifying the maximum value in this window, which is AF in this case. After this, it starts scanning right outside this window. So it takes the byte A2 and compares it against this byte value AF. It checks to see if A2 is greater than or equal to AF. In this case, it's not. So scanning moves ahead to the next byte, which is F4. When we repeat the comparison, we see that F4 actually satisfies this condition, so a chunk boundary is inserted here. And we repeat this process throughout the entire file to divide it into chunks. Okay, so the remaining hashless algorithms I showed here also work using similar principles, but there are slight variations. Okay, so what are vector instructions, the other piece of VectorCDC? These are special CPU instructions with SIMD capabilities, and they've previously been used in math and multimedia applications. So they rely on special CPU vector registers, which come in multiple sizes, 128 to 512 bits wide. And depending on which size you use, your instruction can be classified as one of these families. So let's say I have 4 integers I want to add to 4 other integers. Now, in the regular world, what I would do is use 4 separate integer addition operations. The first to add 10 plus 10, the second to add 11 plus 11, and so on. But if I load them into a vector register, I can use one single vector addition operation to get the results back into another vector register. So instead of using 4 integer operations, you're now using 1 vector operation. So how do we use these to build VectorCDC? Here's a look at our design. In VectorCDC, we identify 2 common phases among all hashless CDC algorithms. The first is the extreme byte search phase, and the second is the range scan phase. In the extreme byte search phase, you're basically looking for an extreme byte in a data region. An extreme byte can be a maximum or a minimum value. To do this, we first begin by packing bytes into vector registers. So let's say we can fit 3 bytes into this vector register here. We would load the next 3 into another one, and so on. So in step 1, we run one vector max or Vmax operation between these registers to obtain the resulting pairwise maximums. So for example, the maximum between byte value 10 and 51 is value 51, which goes to the resulting register. And we repeat this process for the rest of the region to get another resulting register as well. Now in step 2, we run a Vmax operation between these registers. And we keep repeating this process to build a tree. Now, we keep repeating this process until we're left with only one register, which contains the maximum values from the entire region, which we sequentially scan to determine its value. In this case, it's FF. So this is the first phase. The other phase we accelerate is called range scans. Another phase in hashless algorithms is where you serially compare bytes from a data region against a target value using a conditional comparator. To do this, we load the target value into its own vector register by repeating it. And we also load bytes from the data region using pack load, similar to before. We run one vector compare operation to see if any of them satisfy our condition, and if not, we slide ahead and load the next bunch of bytes. And we keep repeating this process until we either find a match or we run out of bytes in the data region. So now this might sound a little bit alien, but let me tie it back to the algorithms I just talked about earlier, right? So if you remember how RAM works, the first part of it was to identify the maximum value in a fixed size window, which is nothing but an extreme byte search. And the second phase was to compare bytes serially against this maximum value, which is nothing but a range scan. So in the VectorCDC universe, RAM is nothing but an extreme byte search phase followed by a range scan phase. And similarly, the other hashless algorithms I talked about can be redesigned using VectorCDC's phases. So what are the advantages of rebuilding these algorithms in using these AVX-friendly methods? To do that, we need to look at our evaluation. For our eval, we use a bunch of diverse datasets such as Rust backups, VM backups, Redis database backups, Linux kernel code, similar to existing literature. We evaluate space savings efficiency, we evaluate speed and throughput, and backwards compatibility. Today, I'll just be looking at speed. And we compare a whole range of alternatives, both hashless and hash-based. All of these are CDC algorithms. And the majority of them are not vector accelerated, except SSCDC, which I showed you at the beginning of today's talk, which is vector accelerated. So what do our results look like? For this experiment, we use our VM backups dataset, and we use 8 kilobyte chunks. The x-axis shows you different CDC algorithms, and the y-axis shows you speed. From the graph here, we see that the fastest variant is fastCDC, which hits close to 2 Gbps. And note that unaccelerated algorithms are represented using solid bars, and vector accelerated ones are represented using pattern bars. So yeah, fastCDC is the fastest, and it's still faster than many of the vector accelerated algorithms, and we have the details about why this is so in our paper. From the graph, we also see that VRAM, which is our VectorCDC accelerated RAM, hits 25 Gbps, which is orders of magnitude faster than all the remaining alternatives out there. In fact, we are 12 to 15 times faster than any other alternative. And this is not just specific to this data set. This result also holds on the other data sets that we've looked at, such as Redis backups. So these are the absolute throughput numbers, but what about speedups? I began today's talk by showing you how SSCDC achieves low speedups on randomized data, and the same trend holds when we look at real data sets as well. SSCDC manages to achieve 1.2 to 1.7 times speedup. But VectorCDC, on the other hand, when we compare it to RAM, which is its unaccelerated counterpart, we see that we achieve a 16 times speedup when using vector instructions. Note that the y-axis on both these graphs are different, and this will become important just in a little bit. So yeah, VectorCDC achieves much higher speedups than SSCDC. And as the axes are different, we see that VRAM is 21 times as fast as SSGear. Okay, so to summarize, data deduplication is used to improve storage efficiency, and CDC algorithms are a critical aspect of deduplication, dictating both space savings as well as end-to-end system throughput. We presented VectorCDC, where we redesign hashless CDC with AVX-friendly techniques to achieve 21 times higher throughput than the state-of-the-art. And most importantly, as I've been saying, accelerating these hashless algorithms with VectorCDC does not have any negative impact on the deduplication space savings. Our code is publicly available on GitHub and can be found either via the URL or the QR code in my slides. And finally, we've been through the artifact evaluation process and received all the badges. So with that, I'd like to thank you for attending my presentation, and I'm open to answering any questions you may have.